Okay, good morning everyone. So we are here to review the main questions and the concepts related to chemical bonding. As mentioned just now, the important thing is to be able to apply your knowledge. And one way to apply your knowledge is always to be asking questions and understanding the underlying concept. Now, the first underlying concept is why bonding? Okay, so you might be asking yourself, what's this question asking about? What on earth do I know about bonding? Why must a particular substance bond? Okay, so why bond? Now, this is a very fundamental question, but yet it's very important to answer. I'm sure you know the answer by now. All your elements will bond so that they achieve a fully filled outermost shell. That is always the purpose of bonding, which is why if you have practiced the ionic and covalent bonding essay questions, don't you notice whenever we ask you explain how a bond forms, explain why a bond forms, regardless of the bonding type, this is always the aim to achieve a fully filled outermost electron shell. The reason is because this achieves stability, right? This is stable. It's the stable noble gas electronic configuration. And this brings us to the next concept. Noble gases are from group 18, right? They have fully filled outermost shells already. That's the reason why noble gases do not form bonds with other elements, because they are already fully filled outermost electron shell. They do not lose, gain, or share any more valence electrons. Okay, so whenever you are asked why are noble gases unreactive, it's not just that they have a fully filled outermost electron shell. Always go on. So what if they have a fully filled outermost electron shell already? So noble gases have a fully filled outermost electron shell, hence they do not lose, gain, or share valence electrons with other elements. Okay, now this is the why bond. The next step is how to bond. So you notice it's about electrons. If it wasn't about electrons, then we wouldn't need to have this lesson, right? So it's about electrons. And the idea is different types of elements will do different things with their electrons. For instance, if you're referring to metals, what can metals do with their electrons? Metals lose valence electrons to form positive ions. If you recall, positive ions are called cations. Okay? Whereas non-metals tend to gain valence electrons to form anions, which are negative ions. So that's one possible way to bond, right? Metallic elements lose valence electrons, while non-metallic elements gain valence electrons to achieve a fully filled outermost electron shell. This you already knew. But between this, you actually have a lot of wisdom. Because metals lost the valence electrons, non-metals gain the valence electrons. We can say that there is a transfer of valence electron from metal to non-metal, right? So that is one way of describing what happens during this particular bonding process. And of course, you should know by now, this is called ionic bonding. Okay, so that's how to bond. Part one, ionic bonding, where you have a metal and a non-metal, and this happens. Okay, now, so let's call this part one, ionic bonding. Of course, there's part two, there's part three as well. Okay, but this is part one. Ionic bonding is between a metallic element and a non-metallic element. And this is possible because metallic elements lose valence electrons while non-metallic elements gain valence electrons. Okay, now, before moving on, a good student, if to know whether you are doing well in chemistry, is From this simple concept, can I predict what the question was going to be? First, you can predict. How do you predict the question? There's one question that we could always ask you, which is, how do you tell from the number of electrons whether something was positive ion or negative ion? If I were to give you the number of protons, electrons, and neutrons, can you tell whether it's a positive ion or negative ion? And the keyword here is lose, right? You are losing valence electrons, right? If you lose valence electrons, that means the electron must be less than the proton. Because you lost valence electrons, therefore, positive ions have fewer or less electrons. Okay, so these are positive ions. On the other hand, a negative ion must have more electrons than protons in the particle. Okay, so that's the idea. The second thing we can ask ourselves on a daily basis is, okay, so now we know about how to bond. Can I explain this in a paragraph using an example? So what examples could you use? You could just think of simple examples such as calcium oxide, sodium chloride, calcium chloride. Whichever elements you choose doesn't make a difference. It's a good daily practice. So for instance, let's just use calcium chloride as an example. You know by now, calcium chloride is CaCl2. This is ionic, right? How does calcium chloride form? So many of you, you have practiced the essay questions. I hope you realize it's helpful. The calcium atom has an electronic configuration of 2882. So it loses 2 valence electrons to form the Ca2 plus ion 288 with a fully filled outermost shell. Now, this is the first point. And this is logical. You could deduce this from the electronic configurations. Just go to the periodic table, find calcium, you could deduce this already, right? But the question now is, many of us, we are not disciplined with our words. You must be disciplined with your word. There is a difference between atom and ion. Atom is 2882 before it lost any valence electrons. That's an atom. But this, you are talking about CaCl2. It's an ionic compound. The ionic compound doesn't have atoms anymore. The ionic compound must be made of the Ca2 plus ion. Which is why you notice whenever you explain things, you will get marks deducted because you're not using the right word. Atom is what you started with, 2882. Ion is the charged particle that is formed after the valence electrons are lost or gained. Okay? So different terms mean different things. It's very important to realize this. Of course, now you can move on. The chlorine atom, which is what you started with, is 287. It gains 1 valence electron to form the Cl minus, the chloride ion. And the purpose is with a fully filled or to achieve a fully filled outermost shell. Now, this is the basic. And you need to know that, hey, it's about atoms losing or gaining valence electrons to become ions. Different words. Okay, now I'm stressing wording now because I noticed that was a common mistake that many of you made during the assignments. Okay, you must be willing to accept this piece of feedback, or else you will notice that your explanations out of 4 marks, you are going to get 0. Just because one word is wrong. The moment one word is wrong, the whole answer is negated. All right, so it's very important to know ionic compounds, ions. Don't talk about other things. All right. Now, but that's not the end. You have only explained how the 2 ions are formed. You now need to go on to explain how do they come together to actually form the whole ionic compound. And this is where you need to mention. So of course, the Ca2 plus and Cl minus ions are oppositely charged. So they are attracted by strong electrostatic forces of attraction between the ions. So you notice again, it's about ions. Okay, so it's between the ions. And lastly, which some of you didn't mention during the essay, it's a specific compound. You know, it's CaCl2, so it's a 1:2 ratio of Ca2 plus and Cl minus. And the structure, giant ionic lattice. Okay, so please take this down. Now, so this is something you can do on a daily basis. Repeat this exercise for another ionic compound of your choice. Sodium chloride, magnesium chloride, magnesium nitride. Okay, the world is the limit. Essentially, I can vary the compound, but the answer, the understanding remains the same. Okay. Okay, once I'm done copying, you can give me a reaction. Otherwise, if you have questions, you could also ask. So we have covered how to bond, which is ionic bonding. This is the model answer, if you like, for the first question of your essay. Having said that, the first question on the essay list, I think was calcium oxide, not calcium chloride. But yes, this should be the structure of the answer. Okay. Now, the next step to doing well in pure chem is, of course, to manage your time. You need to watch the time and not go overboard with the time or do it too slowly. But also importantly, you need to give good quality answers. So something that I always do after writing an explanation out is to reread my answer within time limits, of course. I do not drag my time. But if I still have a little bit of time, I will reread after every single part to ensure I've written a high quality answer. And a high quality answer here, you can see, goes beyond just talking about losing and gaining valence electrons. A high quality answer can even go on to talk about forces of attraction between ions, can even go about talking about the ratio of the two ions present. All right, this is a very high quality answer. And that's what you need to aim for. How do you become faster? Now, the way to become faster is not to do more TYS. The best TYS is your daily experience. Do you ask yourself this on a daily basis? Could you do this for, say, another ionic compound, sodium chloride, potassium oxide, so on and so forth? If you can do it on a daily basis, you'll become very, very good at it, even without doing the TYS per se. All right. Now, we are now going to move on to the, of course, dot and cross diagrams. How do you draw dot and cross diagrams? We're going to use calcium chloride since we have already done it. Now, so calcium chloride is ionic. So we will have to draw the Ca2 plus ion. Remember, you're asked to draw ionic compounds, so it's ion. Some of you, for the assignment, you still drew the atom, which is incorrect. The ion Ca2 plus is 288, which is what I'm drawing now. Okay, 288. Those of you who drew the atom 2882, that means your understanding of the words is not disciplined enough. You need to know there's a difference between atom 2882, ion 288. Okay? The ion is after you have lost the valence electron, after you have acquired the charge, which is why you can see there's a square bracket and the charge. Now it's CaCl2 because obviously the 2 plus charge must be balanced out by the 2 times 1 minus charge. So chloride is only Cl1 minus, hence you need to have 2 of it. Now, another way to see this is chlorine gains 1 valence electron, while calcium loses 2. Hence, you need to ensure that you got 2 chlorines to gain 1 electron each from the calcium ion. Okay, so this is CaCl2. Now, it is also very important to notice we used a different symbol for the electron that is gained. Now, this is of course only in ionic bonding, because in ionic bonding, we talk about loss and gain of valence electrons. In covalent bonding, we are not going to talk about this, because in covalent bonding, we do different things to the electrons. So you see, the concept must be very clear. You have to construct a schema in your head. What do I do with the electron? Here, I'm talking about losing and gaining. That is ionic bonding. Okay? Now, you notice as well, in explaining, we don't say the Ca2 plus and Cl minus are attracted by ionic bonds. We do not say ionic bonds. We say strong electrostatic forces of attraction between ions. Why? If we just said strong ionic bonds, is it factually wrong? No, it's not factually wrong. It's correct, right? It's called ionic bonds, ma. But you are not explaining what is ionic bonds. The question is asking you to explain the bonding. If you just wrote ionic bonds, you are not explaining the bonding. All right. So instead of writing strong ionic bonds, you need to ensure you always write strong electrostatic forces of attraction between ions so that you are explaining the bonding type itself. Okay. Which is why you see in your assignment, if you wrote strong ionic bonds, I actually marked it wrong because you are not explaining, you're not giving a good quality answer already. So don't go for shortcuts, really go for conceptual understanding and depth. All right, so this is a dot and cross diagram I've drawn for you. This is what an ionic compounds dot and cross diagram will look like. And remember, ionic compounds, giant ionic lattice, is formed when your elements lose and gain valence electrons. So lose and gain or transfer valence electrons. Okay, now let's do some questions regarding the lattice itself. Okay, this is from your notes. So first we have sodium chloride. So how do you prove that from this lattice there is NaCl? Well, the way to do this, of course, is to do counting. If we just counted how many Cl minus ions there are in this particular unit of the lattice, you count, there is 14 Cl minus, right? Sodium, there's 13 Na plus. So you can see the ratio is about 1:1. About 1:1. Now, it's not going to be exactly 1:1 because you are only shown part of the lattice. There are other parts of the whole lattice structure which cannot be represented, of course, because it goes on forever. So even with just this unit of the lattice, you can see there is more or less a 1:1 ratio. Hence, the formula is NaCl. Now, could this have been another ionic compound instead of NaCl? The answer is yes. It could also have been KCl. It could also have been MgO. It could also have been MgS. But it could not have been MgCl2. Why? It's because of the ratio. This is, of course, a 1:2 ratio, right? Whereas all these are 1:1 ratios. So by counting and getting the ratio from the lattice, you can actually work out which formula are possible for this structure, which formula are not possible. Okay. Now, the next question regarding the lattice, okay, that's also from your notes. A compound contains two elements, metal F, non-metal G. Make it a point to highlight chemical names, it helps. So F is a metal, G is a non-metal. I will go on and write, a metal loses electron, so it's a positive ion. Metals form positive ions, whereas non-metals gain electrons to form negative ions. Okay? So I will write this down. The purpose of writing this down also is to jog my memory. So like I said, many of you, you tend to just stare at the question. Now, staring at the question is not going to work. Even for me, it doesn't work. You will need to write down, oh, metal, what do I remember about metal and non-metal? Write it down. It helps. Of course, you are told this is a lattice of positive and negative ions, a giant ionic lattice. It's an ionic compound, metal and non-metal. The next part is to highlight numbers. Each positive ion, meaning one positive ion, is surrounded by 6 negative ions. Whereas each negative ion is surrounded by 3 positive ions. Okay, so let's process this. Okay. Okay, so let's process this. Okay. So one positive, positive attracts 6 negative. But one negative only attracts 3 positive ions. There is a relationship in the numbers, right? Each positive ion attracts 6 other ions around it. So this positive ion must be doubly powerful, doubly charged. It must be double in charge. If not, how to attract so many things to come to you? It must be powerful in attracting it, right? So you can conclude that the positive ion must be doubly powerful, doubly charged compared to the negative ion, meaning 2 plus versus 1 minus. Hence, who will form positive? Is it F or is it G? So now you go back to what you have written. See, if you have written it out at the start, you will know. Oh, F is the metal. So F must be the positive ion. So F2 plus, G minus. And once you have that, the formula is just FG2. So you can see the amount of annotations and thinking that goes into such questions, even though it might be just an MCQ that's 1 mark. All right, it's very, very important to write things out as they come along so that you really make your thinking visible. So don't just leave the sentences as they are. Really write out 1 positive attracts 6 negative. 1 negative only attracted 3 positive. So the positive must be doubly powerful, doubly charged, 2 positive. 2 plus charge. Okay. Now I shall leave this here for a while for you to take this down. And if you have any questions, also feel free to ask in the Q&A. Okay. Okay. Any questions, or if you're okay for me to move on to the properties of the giant ionic lattices? Okay, if you're okay to move on, also just let me know as well so that I know that you are ready. Okay, so you must understand how to do such questions. It's not as simple as just, oh, I know it's an ionic compound. No, because for the pure, you need to know the lattices very, very well. Okay. Now, moving on, of course, is the properties. Many students just resort to remembering, but don't just remember. Now, what properties have you learned? You have learned melting point and boiling point. You have learned electrical conductivity. Okay, I would say these are the 2 main ones. Of course, there's also solubility. Solubility, that one you don't have to learn how to explain. Okay, we will do more on solubility and dissolving probably next year when we do energy changes. But for now, we focus on these 2. You will need to know melting and boiling as a concept. Melting and boiling are processes to change the states. Solid to liquid is melting. Liquid to gas is boiling. Now, in order to do this change in state, you need to take in energy. So the idea is take in energy, right? That's obvious. You will need to heat something up in order for it to melt or boil. Take in energy from the surroundings, but to do what? The energy is used for something. The energy is used, we know, because in the gaseous state, the particles are further away than in the liquid state. So you need to make them further away from one another. To do that, we will need to overcome the forces of attraction. So the idea behind melting and boiling point explanations is always about how much energy is taken in order to overcome what type of forces of attraction. Okay, so this is a central concept. Melting and boiling point depends on the forces of attraction, which you are overcoming. Then we come to electrical conductivity. So in Sec 2, you did electricity. You learn this concept of current. Current is the rate of flow of electrical charge. So the idea is charged. Do you have anything which is charged? But beyond that, do we have anything that is charged that can flow? So the idea is free to move, charged particles. So you got to ask yourself, are they free to move? Are they charged? What is charged? There is ions, right? So ionic compounds have ions. The question is, are they free to move? Okay. Now, the next type of charged particles could very well be delocalized electrons. So you need to know when to use which one. Ions is, of course, for the giant ionic lattice, right? If not, why call it ions? Delocalized electrons is for metallic lattice. And graphite. So you will need to use the right words for the right structures. Okay. Now, so instead of just memorizing set explanations, you will need to apply. Because like I said, I may not test you something familiar. In fact, we will not usually give you something that's directly out of the textbook. So you will need to realize that, hey, there are some of these concepts. Okay. Now, you notice I've written delocalized electrons and as well as free to move. They are not the same thing. So you will need to write both. The delocalized electrons are free to move. Why? Delocalized just means the electrons are not fixed to one atom or ion. The electrons are not fixed in place, basically. Hence, just by saying delocalized, you have not captured the idea of freedom of movement. So you will need to write both. The delocalized electrons are free to move or can move freely. However, throughout the metallic lattice or along the layers of carbon atoms in graphite. So you will need to write both for delocalized electrons. So we'll see that in a short while. So please learn the difference in these words. That's why during the lessons, my question is, when we taught delocalized electrons, did you ask what it meant? Did you go home and think through what this word meant? It cannot be just thinking through before the O-level exam. You will need to think through on a daily basis. All right? So the reason why I go through this first before going through the answers for ionic compound is I want you to realize that the explanations for melting and boiling point and electrical conductivity follow a set pattern. They follow the same concept. So you need to know the concept. The concept is important. All right. So now we go, of course, to the giant ionic lattice. So specifically, I'm not talking about delocalized electron. Delocalized electron is not giant ionic lattice. Delocalized electron is not giant ionic lattice. Delocalized electron is for graphite and metallic lattice. Separate understanding, separate. All right, important. Because the last thing you want is to mix it up. Giant ionic lattice, ions. Full stop. Everything is ions, nothing else. Okay? Take the cue from the name, which is why you always start off your explanation with the name of the structure. Because that gives you the cue how to continue. The moment you don't write the structure correctly, your answer goes haywire. All right. So now, giant ionic lattice structures have high melting and boiling point. And how would you answer this? Why? Because they have giant ionic lattice structure. Right? So then next step is talk about forces of attraction. There are strong between the two ions. Okay, so you can say oppositely charged ions, or you could even name what the ions are. So like just now we had Ca2 plus and Cl minus, right? Which require a lot of energy to overcome. Okay, so that's giant ionic lattice. I think it's a standard answer. You have seen this a number of times. Then how about electrical conductivity? Now, electrical conductivity, it, because it depends on its state. It does not conduct electricity in the solid state, but good electrical conductivity in the molten and aqueous states. Okay, so this is very unique to ionic compounds. It's quite unique, right? Because no other type of structure will have this property, where in the solid state it doesn't conduct, but somehow when you have melted or dissolved it, it conducts. So again, you start off, they have giant ionic lattice structure. So it grounds your understanding. Oh, I need to talk about ions. So how about the ions? Ions are charged, great, charged. However, are they free to move? Can move freely or not? So that leads you to your next answer. The ions in the solid state are held in fixed positions by the strong electrostatic forces of attraction and cannot move freely. They are not free to move. All right, so they cannot move freely if they were in the solid state. Therefore, the ions cannot move freely, hence the ionic compound doesn't conduct electricity in the solid state. Then don't forget the molten and aqueous states. In the molten and aqueous states, the ions are free to move, can move freely, as the strong electrostatic forces of attraction between ions have been overcome. All right? Now, it might look like a whole wall of text to memorize, but don't memorize. The concept is, hey, the ions are charged, but hey, are they free to move? Ask yourself that. Ask yourself that. When you ask yourself that, you can always construct this explanation from scratch. All right? Now, for pure, of course, you need to know this. This is fundamental explanations. You must know this. All right? But what's also important is to do reverse engineering. What do I mean by reverse engineering? What if I didn't tell you this was ionic? Can you, based on the melting points and electrical conductivity in different states, work out that this is ionic lattice structure? So I think that's important. Can you take a step back after you have finished copying and look at the two properties? I hope you have copied them side by side. Take a step back. How do I tell that this is an ionic lattice structure if I was given the melting point and electrical conductivity? Can you do that? Will you recognize that a high melting point plus it doesn't conduct in the solid state but conducts very well in the aqueous or molten state mean it's ionic lattice? Now, then take a step back. Now there is an ionic lattice. Can you go backwards and work out? Oh, so how is it formed? Do I know that this is a property of metals with a non-metal? All right. So taking a step back is important after you finish each concept and each topic. Okay, so this is what I call taking a step back. Now we have finished ionic lattice. As you can see, ionic compounds and ionic lattice, that's all the content you need to know. But I can set many different things that are interesting from this. Okay, so it's based on simple concepts, you can go to a very far place. Okay, so now moving on. Of course, after the ionic bonding, there's how to bond part 2, which is of course covalent bonding. All right. So before I move on to covalent bonding, can I just ensure everyone is okay so far? And if you have any questions that I can help to answer, please ask them inside the Q&A. All right. Any questions? Or are we okay to move on? Okay. So now let's move on to how to bond part 2, which is what we'll finish today. Okay. So today we'll only do the giant ionic lattice, simple molecular structure, and giant molecular lattice. So how to bond, part 2. How to bond, part 2 involves non-metal with a non-metal, right? Both are non-metals. So if both are non-metals, you could not possibly have one of them lose a valence electron. They don't want to do that. They want to gain valence electrons if they could. But since both are non-metals and both would like more valence electrons, they could just make do and share valence electrons with one another. All right. Of course, the best example here, CO2, right? CO2 is the simplest example. Okay. But today, perhaps let's do something else, which is more suited to your essay question that the list I've given you. Today, let's do carbon and chlorine. So, in the essay questions that I've given you, I asked you about how carbon bonds to chlorine, I think. So, how do you explain that? Now, the carbon atom is 2, 4. Okay, you can work that out from periodic table. This means that it needs 4 more valence electrons, right? In order to achieve a fully filled outermost shell. Okay. Now you can repeat the same analysis with chlorine, right? Okay, by now I'm sure you know it's very repetitive. Actually, it's really repetitive. So chlorine just needs 1 more valence electron. Now, so this is outlining what is going to happen between carbon and chlorine. And this brings us to the important point. Carbon needs 4 more, chlorine needs 1 more. Hence, the, maybe we should say each or one carbon atom shares 4 valence electrons with 4 chlorine atoms to form a CCl4 molecule. It's CCl4 because carbon shares 4 while chlorine only shares 1. Therefore, I need 4 chlorine atoms in order for carbon to share 4 electrons, 1 electron shared with each chlorine. Okay? Now, after sharing, it's called a molecule. So what have you learned? You have learned the A, the I, the M. Atom. I give you an example. Atom, chlorine, 287. Ion, got charge, 288. Molecule, CCl4, covalent. So it's helpful to remind yourself the AIM. There's a difference, different words, different meanings. All right. So you can use chlorine as an example. Cl, atom. Cl minus, ion. CCl4, covalent molecule. Okay. Now that's not it yet. So it forms a CCl4 molecule. Then what's next? You need to talk about the structure. Many CCl4 molecules are attracted by weak intermolecular forces of attraction between molecules. This is called the simple molecular structure. Okay, so that's CCl4 for you. It's made up of many small CCl4 molecules which are attracted to one another by the intermolecular forces of attraction between the molecules themselves. Okay, now the simple molecular structure is true for like 95% of all covalent substances. So if there's covalent bonding and sharing of valence electrons, all right, it's 95% going to be simple molecular. The 5% left, of course, is the giant molecular lattice structure. Giant molecular lattice only applies to about 5% of covalent substances, and the 5% are best learned by heart, meaning you will need to know, oh, diamond is a giant molecular lattice structure. Graphite has a giant molecular lattice structure. Silicon dioxide is also a giant molecular lattice structure. So you will need to learn the giant molecular lattices one by heart, because the rest, which have covalent bonding, are more likely to be simple molecular. Okay? Giant molecular is more of things that you need to learn, case studies that you have to learn. All right? So now let's take the simple molecular structure first and draw the dot and cross diagram for CCl4. Now, dot and cross diagrams. Sometimes we will ask for all electrons. Sometimes we are going to ask for just the outer shell. So let's assume the question has told me to draw outer shell only. So I have C in the center because there is only one carbon atom. That means I have 4 Cl atoms sharing valence electrons with the carbon. All right, we just said chlorine needs one more valence electron. Hence, it shares one. Now, sharing one means I share one with you, you share one back with me. So that's why it's always dot and cross, even though sharing one. All right. So now that's not the end. You need to ensure that you have accounted for all the electrons. Chlorine is 287, right? If it's 287, you have just shared one electron with carbon. So each chlorine shared one electron with carbon. So each chlorine should have 6 electrons left behind. How did you get 6? 7 valence electrons minus away 1 that you have shared. You are left with 6 valence electrons on each chlorine atom which are not shared. Don't forget the 6. Now, this applies to every chlorine atom. So they have 4 chlorine atoms here. So please make sure you repeat the 6 valence electrons on each chlorine atom. How about carbon? Now, carbon is 2, 4. You have written that down. Carbon has shared 4 valence electrons. So carbon has 4 valence electrons. It has shared all 4. Therefore, there are no more valence electrons left that are not shared. Hence, carbon is already completed. It's done. Okay, so this is showing outer shell electron only, or valence electron only. The question will say that, so you need to read the question. Okay, it is not always true that we get you to draw outer shell only. You need to read the question. Now, there was a question that came in. How do you know if the intermolecular forces are strong or weak? Intermolecular forces of attraction are always weak. They are always weak. If you are reading the enrichment notes and you read about hydrogen bonding are still weak intermolecular forces of attraction. They are just the strongest of the weak. They are still weak. All right. So intermolecular forces are always weak. Always. Always. Okay. Now, so that is the simple molecular structure. So I'm sure you can predict what's next is the properties, right? So simple molecular structure. Simple molecular structure. Simple molecular structure, very low melting and boiling point. Very low, okay, not just low actually, very low. All right. Generally, they are gases at room temperature and pressure gases. They are negation state. Another way to say they are gases or they form gases easily, they are volatile. So CCl4 is volatile. CCl4 is a liquid at room temperature, but if you leave it out in the open, this liquid CCl4 evaporates very, very quickly. If you went for lunch and came back, in 30 minutes, it would have evaporated completely. All right, and why is that so? Again, always start off your explanation with the structure. Because if you write the structure's name, you are more likely to know what to say next. Because it's simple molecular, you talk about molecules. Molecular, molecules. So there are weak intermolecular forces of attraction between, in this case, the CCl4 molecules. Okay, which require a low amount of energy or very little energy to overcome. So what do you notice? Again, it's about forces of attraction. That's why the concept is important. The concept is melting and boiling points depends on forces of attraction. Okay. Now, how low is low? Generally speaking, something less than 500 degrees Celsius is low. Generally speaking, it's not a rule, it's just a guideline. All right, so there's low melting and boiling points. Now we go on to electrical conductivity. There's no electrical conductivity. That means it doesn't conduct electricity at all in all states. That means regardless of solid, liquid, gas, aqueous, it doesn't matter. So long as it's a simple molecular structure, it will not conduct electricity. So again, CCl4 is a good example. CCl4 has a simple molecular structure. Okay, so how do I explain electricity, electrical conductivity? It's about charged particles that are free to move. So now think, are molecules charged? We learned just now, right? Things that are charged, ions, delocalized electrons. Does it look like it has ions? No, it's simple molecular. There's no ions, no ionic bonding, nothing, no ions. Does it look like it has delocalized electron? The CCl4, look, the electrons are drawn on each atom. They are fixed to that particular chlorine atom, or they are shared between carbon and chlorine. So the electrons are definitely fixed where they are. So there are no free moving ions, because it's not ionic, or electrons, because it doesn't have delocalized electrons. So there are no free moving ions or electrons to conduct electricity. Okay, so that's simple molecular structure completed. Now, so again, it's good to take a step back and think, oh, so that means if I am told they don't conduct electricity in all state, and I'm told it has a low melting or boiling point, that means it's simple molecular. Exactly. So just by looking at the melting and boiling points and the electrical conductivity, we can work out a simple molecular. All right. Now, before we go on to giant molecular lattice, I hope you again take a step back and look at what you have copied. I hope you can write out this analysis, how a simple molecule like CCl4 is formed. And now, a good practice to ask yourself is, how about not CCl4? Can I just choose two non-metals and just randomly think what their formula would be, as well as how do I draw their dot and cross diagram using only outer shell electron? So for instance, if I didn't do CCl4, I instead did phosphorus and chlorine, P and Cl, phosphorus and chlorine. How will this assay change? How will the dot and cross diagram change? What is the formula of the covalent substance, covalent molecule formed by phosphorus and chlorine? Can I work that out? That is the challenge for you every day. When you look at the periodic table, just choose random non-metals and think what the formula would be. Think how many electrons would they share with one another. Can you write this out based on the two elements that you have chosen? Okay, can boron, same. How about boron? Someone just asked. A good question. Boron and chlorine, right? And these are the atypical, the not so usual dot and cross. Boron is 2,3, chlorine is 2,8,7. So by right, boron needs 5 more electrons, right? Indeed, it needs 5 more electrons, but it doesn't have so many to share. Covalent bonding is equal sharing, you know. That means boron has 3 electrons, so it will share all 3, right? But even after sharing all 3, is boron truly stable? Has it achieved the fully filled outermost electron shell? I'm sure you'll agree with me, it hasn't achieved that fully filled outermost shell. Can boron obtain more electrons so that it achieves a fully filled outermost electron shell? Yes, it could, but not here, not from this. Boron has already shared all 3 of its valence electrons. Hence, boron forms BCl3. And BCl3 is interesting because boron is electron deficient. So if you looked at your notes, there was a whole section dedicated to such dot and cross diagrams for uh, atoms which are electron deficient. So boron is an example. Aluminium is another example. Aluminium forms AlCl3. All right, molecules. Okay, so boron is electron deficient. So it's still lacking electrons, even after sharing electrons with chlorine. Okay, but could it get more electrons as it is? No, because it has already exhausted all 3 of its valence electrons. So boron could get electrons, the BCl3s, boron and BCl3 could get more electrons from somewhere else, but that somewhere else is part 2 of the story. All right, it needs to react with something to get more electrons. But if I'm just looking at BCl3, that's it. That's the max it could do. Okay? So the challenge for you is, can you do this exercise every day? So now you're asking about boron. Can you ask yourself about other elements? Phosphorus, sulfur, iodine. Could iodine bond to chlorine? Yes. Will it be sharing? Yes, because iodine is also a non-metal. So what will the formula of iodine and chlorine sharing electrons forming a molecule be like? Ask yourself these questions. All right. Then someone else, could there be dative covalent bonds with the boron? Yes, there could be dative covalent bonding. All right. So if you have done the database questions as well as the enrichment, you would have done dative covalent bonding. So BCl3 is still electron deficient, right? It needs to get electrons somewhere. So it will dative covalent bond. So what happens is like that. This is BCl3, right? I could draw another BCl3. Now the chlorine, you notice, still has valence electrons, sorry. there are actually 6 valence electrons not shared, right? So what happened is, sorry, maybe I shouldn't draw like that. Sorry. I should draw like that. So the chlorines could dative covalent bond to the boron. Okay, but dative covalent bonding is not in the O-level syllabus, but I included it in the enrichment. So please read, okay? Please read, because it could be the database question, right? Now, if you are lost on what dative covalent bonding is, it's time to read the database questions and the enrichment, okay? So dative covalent bonding means the covalent bonds electrons, both electrons came from the same atom. In this case, both electrons came from chlorine, because boron has nothing more to give. But you notice, for dative covalent bonds to form, the 2 electrons came from the chlorine of another molecule, not the same molecule. So you cannot have dative covalent bonding within just the one molecule. It must be from another molecule, okay, for BCl3. All right. Now, this is also a good exercise to do on a daily basis. When you are taught this in class, do you notice I teach at a relatively slow pace? In one lesson, you may literally only do 2 concepts at most, and that's the purpose. That's why after every lesson, you need to read through so that you make the links. Remember when we did covalent bonding, I spent one lesson doing the standard dot and cross diagram like CCl4, CO2. I spent the second lesson doing the unusual ones like BCl3. And then later on, I did the enrichment where I did the dative covalent bonding. 3 different lessons. The idea was after every lesson for you to make the links. When you make the links, your understanding of chemistry is more rich. And hence your studying will be much easier. And that's why chemistry is a daily thing. So after the lesson today, you should ask yourself, what's the formula formed by iodine and chlorine? If iodine and chlorine forms a molecule, what's the formula? Then you can go online and check. Are you correct? Phosphorus and chlorine, are you correct? Okay, try doing this analysis yourself. Don't be confined by the notes CO2, CH4, CCl4. Don't be confined by that. Ask yourself, in the vast periodic table, how could it form? Okay, if you can do that, that's when you know you will get an A1. If you cannot do that correctly, that's when you know your level of achievement has not reached A1 yet. All right. Now that's simple molecular. The last one we'll move on to is giant molecular. Now, today we are going to focus on diamond and graphite. Tomorrow I will do a revision and go through SiO2. Now, we have spoken about giant molecular, in particular diamond and graphite at length. Okay, I'm not going to redraw diamond and graphite. I'm not. I think what's very important for you to know is that they are allotropes of carbon. That means both diamond and graphite, they are actually carbon. They contain carbon atoms. Okay, just that the carbon atoms are connected, bonded differently. Therefore, the structure looks different, and hence they have different properties. Okay, but the idea is both of them contain carbon atoms. Now, giant molecular lattice means atoms covalently bonded together. But they are covalently bonded not to form small molecules. It's to form one giant molecule. So it's really singular. One molecule. Don't have molecules. All right. So diamond, if you want a quick drawing, it looks like that. Right? Where each dot is one carbon atom, essentially. Okay. Now, so this is a diamond structure. Okay. So of course it goes on and on and on. So please don't be mistaken. It goes on and on and on and on and on and on and on. All right. So the idea is each carbon atom is bonded to 4 other carbon atoms. One is to 4. Now, So what is the impact of each carbon atom bonded to 4 other carbon atoms? There are a few impacts. The first impact means all the valence electrons are used for bonding. Or you could say all the valence electrons of carbon are shared. So this is where concept comes in. Oh, so I've shared all the valence electrons. They are like in the covalent bonds. They are between the carbon atoms. They are in the bonds. They are inside the sharing. So there will not be any delocalized electrons, right? If there are no delocalized electrons at all, there is no electrical conductivity. So whether solid, liquid, or gas, diamond is not going to conduct electricity because there's no delocalized electrons present. Next, diamond must be strong and hard. Diamond must have a very high, not just high actually. Diamond has a very high melting point. Again, what has this got to do with diamond structure? There are forces of attraction. It's a giant molecular lattice. There are strong covalent bonds between the carbon atoms. A lot of energy to overcome these covalent bonds. Oh, why is it covalent bond now? Just now simple molecular, don't talk about covalent bond. Because in simple molecular, there is a weaker force called the weak intermolecular force of attraction between molecules. Plural. This one no plural. It's singular. So there's no weak intermolecular forces to talk about for diamond because it's one giant molecule. So the only force you could overcome will be the strong covalent bonds. So that's where the concept comes in. They are different. Just now was molecules. This is not. This is one giant molecule. Therefore, the only forces you have are strong covalent bonds between the atoms. All right. And that the strength, the hardness, all right. That leads to the high melting point. All right. Now, so you notice the localized electrons are important. So just now, like CCl4, the electrons are not delocalized. The electrons are on the Cl, right? They cannot move to the carbon without command. Similarly, ionic compound, they got electrons, but the electrons, are they delocalized? Could the electrons jump from Ca2 plus to Cl minus again? No, the electrons will stay where they are. So delocalized means the electrons can move from atom to atom, ion to ion, which is not the case in diamond. All right, it's not the case. So not any electrons can be delocalized. Only some electrons can be delocalized. Okay. So even though you have drawn valence electrons not used for bonding, those are not delocalized electrons because they are fixed onto the chlorine atoms. So how do you know when they can be delocalized? Okay, the idea is there must be a mechanism for them to move. And so we move to graphite now. So in graphite, yes, there's delocalized electron because each carbon atom is covalently bonded to 3 other carbon atoms. So there is one valence electron not used for bonding. But how come this one can be delocalized now? So this goes back to the structure. Graphite looks like that. Okay, I'm drawing hexagons. I'll try my best to not make a mistake. The idea is because it forms hexagonal, flat layers, the electrons, I'm just drawing 3, but there are more, okay? Each carbon atom has 1 valence electron. I draw 3 so that the diagram doesn't get too messy. The electrons can move freely along the flat layer. So now to answer your question, how come not all valence electrons can be delocalized? Number one, to be delocalized, the geometry of the molecule must be flat. CCl4 is not flat. All right. In fact, most molecules are not flat. They are three-dimensional. Number two, the energy must be sufficient for them to be delocalized. All right. So these valence electrons in graphite can be delocalized because number one, graphite is flat layers. Number two, they have sufficient energy at room temperature. Okay. So yes, graphite has delocalized electrons. And hence, graphite is a good conductor of electricity at room temperature. Graphite doesn't need additional energy at room temperature for the electrons to move freely. All right. So remember, delocalized electrons to move freely, yeah, must write both. Delocalized alone doesn't mean move freely. Delocalized just means it's not fixed. Move freely is the idea of movement. All right. So because graphite has delocalized electrons to move freely along each layer, okay, we can add on along each layer in graphite. Hence, it's a good conductor of electricity, doesn't need additional energy to conduct electricity. All right. So that's a good question. Not all valence electrons can be delocalized. Even if they are not shared, not all valence electrons are delocalized because you need to have a particular geometry, which graphite has. And finally, graphite has a high melting point, and the explanation is the same. Then you'll be wondering, but graphite has layers which are bonded or attracted by weak intermolecular forces, right? Yes. So now this goes back to the concept of melting. Melting means I need the particles to separate. To separate, is it sufficient to just overcome the weak intermolecular forces between the layers? So if I were to separate layer by layer, have I melted the graphite? The answer is no, right? Because the atoms themselves are still bonded by strong covalent bonds. All right. So in order for graphite to melt and all the particles to move freely, I need to overcome the strong covalent bonds as well. Okay. Now, graphite is soft and slippery, not strong and hard. Because soft and slippery doesn't need melting. To be soft and slippery, you just need the layers to fall off. How do layers fall off? Weak intermolecular forces of attraction between the layers. Right? And hence, they very little energy to overcome. All right. Now, all this was summarized in one page in your notes, and that's the purpose, so that you see it side by side. And my final question to everyone before I end today's lesson here is, when you learn this, did it occur to you to read that one page again and again every single day for that week, for 2 weeks, for 1 month? If you thought that pure chem you could study just before the WA, you can, but it won't make it enjoyable. The best way to study pure chem well is to enjoy it. And to enjoy it, you need to read it every day. Okay? So when I was your age, or maybe even younger than you, when I started learning chemistry at Sec 1, because I was in a competition, so I have to learn all these things myself. When I started learning in Sec 1, I read it every day, you know. This whole topic on bonding took me, I recall, the entire term 2 in Sec 1. No one taught me it. I had to self-study. Okay, my teachers didn't teach me bonding because I was in Sec 1. Sec 1, you don't learn this. So I was in Sec 1, I took the textbook and I read it every single day before I slept. Okay. I read it before my CCA while waiting for my CCA to start. All right. So is that something that you would like to do before your CCA starts? Even if it's just 10 minutes before it starts, you could read something. And as you read, you will start appreciating the words more and more. Oh, so delocalize means this, move freely means that. You will also appreciate, oh, not all valence electrons can be delocalized, even if they're not shared. You will also start appreciating the nuance behind it. Okay, so I think it's very important, really, to change the way we study. So, like, for example, you have just done molar gas volume with me in class. Have you gone home to read up? about how did we achieve this number of 24 DMQ. I wrote in the notes, right, it's because of the ideal gas equation. Did you Google what is an ideal gas? Because if you do that, your learning becomes much richer. And then you will never ever have to study. No need to log in to study for pure chem. There is no log in, no need. Because every day has become pure chem. Your life has become chemistry. Chemistry has become your life. It sounds cliche, it sounds funny, but it's true. All right? It's true. Chemistry is not hard if you think about it every day. Okay, so of course, some of my colleagues will think that I'm weird for saying this because not everyone learns chemistry that way. It's true, but if you truly find it important and you truly find it interesting, then you will make it that way. All right? Can? So I'll be honest, even when I take aeroplanes, I think of chemistry. I think of what the aeroplanes are made of, what are the windows made of. Nowadays, we even have windows. You press the button, you can dim the windows, right? You don't even need window shades anymore on an aeroplane. Chemistry. There must be some chemistry behind the material used to make the windows of aeroplanes, right? Yeah. Then I think about the fuel that's being burned, how much CO2 is it generated. You could do more concept calculations, right? To find out the amount of CO2 emitted by an aeroplane and hence the mass of the CO2. You have all this at your fingertips. All you need is a calculator. Okay? So these are things that you think of. And when you think like that, honestly, you don't have to study for pure chem anymore because chemistry is your life now. All right? Okay, so let me end the recording here. And if you have any questions, please continue to ask. Okay?